So there's two different terms that people mix up, radioactive and radiation. So if something is radioactive, it actually means it releases radiation. So if you think of uranium there, uranium is a radioactive element because its atoms or its nuclei release radiation. And the radiation they actually release is a type of alpha particle. It also actually changes to another element. It changes to another element while releasing an alpha particle, and that's the radiation. That's the particle coming off, and that's the stuff that can be dangerous to us. Now there are three key types of radiation. You've got alpha, you've got beta, and you've got gamma. Okay? Alphabet comes from the Greek alpha beta. Okay? So they're the three key types. Alpha is a helium nucleus, He42. There's two types of beta. You can get beta plus and you get beta minus. One is actually an electron, the negative version, which we've actually heard of before. Now this is a lot faster, we're going to come back to that one later. And there's one called a positron, which is antimatter. And a gamma ray is a high energy light with no mass. Okay, so there are three key types. There's also neutrons as well, and you can get spontaneous fission that release neutrons. We're going to look at those over the next coming lessons. So radiation is the stuff that comes off. Radioactive means it actually is going to release radiation because it's unstable. And there's a few reasons why it could be an unstable element or an unstable nucleus. So let's have a look at that. Now, as a general rule of thumb here, when you look at the elements in the periodic table, most of the smaller elements that haven't got as many protons, say up to about 25, 30, have roughly a 1-to-1 ratio. And you'll follow there's a line of stability for the stable elements then that pretty closely follows that line of 1-to-1. Okay, the stable element versions there pretty much follow 1-to-1 as a ratio there. And then once it gets passed around here, because there's so many protons in the nucleus, they actually normally have more neutrons in there when they're stable, and you could think of it as being, it separates the protons a bit further away and reduces their overall repulsion due to the positive charges repelling each other. So this line of stability, if you like, starts to climb, and the ratio of neutrons becomes higher than protons, and you can sort of think of numbers as 1 to 1.4 even. Okay? And that sort of helps with these larger number of protons that are repelling. Now it turns out that when you get to about 83 as a number of protons here, these are protons along here, okay, and neutrons up the side, when you get to about the 83rd one, that's about as heavy as you're allowed to get. Any more than that, you've just got too many protons in there and too much total electrostatic pushing on each of the protons to actually be held together stably by the nuclear force, even with the extra neutrons. So from here on, there's nothing stable there. But as a general rule, it's about 1-to-1 down there, and then it starts to rise after that, up to a limit here. If these are too large, as a general rule of thumb, they will actually release the largest particle they can, alpha particle radiation. And that will change the type of nucleus down by 2 protons and 2 neutrons altogether. So you're going to spit out 2 protons and 2 neutrons and change your parent nucleus to a smaller daughter because that's come off. So that's your alpha particle radiation. So what we're saying here is that things that are radioactive are going to release radiation because they're not stable, and they're going to become more stable by spitting out the radiation. The small ones tend to be a 1-to-1 ratio, neutrons to protons, okay? But the larger nuclei have a greater number of neutrons, and that helps to separate the actual protons to a greater distance while providing an equal nuclear force, okay? That will reduce the total repulsion, as I said. Here are some typical ratios then, 1-to-1 early on, rises to 1.36 or even 1.54 to 1, so it gets quite high there. But as I said, once you get past about 83, your line of stability here, this black line stops. Anything past that will be unstable, become alpha. Now, just for future reference, it turns out you get beta minus if you're above the line of stability in here, and you tend to get beta plus there, if you're below the line of stability, and we're going to look at why it would do that, okay? But it's all to come and to get to that correct ratio of neutrons to protons for stability. So here's an example of alpha decay. What we've got here is you've got uranium, which we've already discussed, releasing thorium, and alpha is a helium nucleus, all right? And that gives a good reduction in the size of the daughter. Now, when you check alpha particle tracks here, we know they're coming off at high speed, but it turns out that they come off at discrete lengths. Some come at this length, the expected length with the expected energy. Some are a bit shorter, a discrete length shorter, and even shorter than that, another discrete length. So it's not a range of lengths that are continuous here, there are discrete lengths of the tracks. Now that actually means that the discrete energy is missing from those alpha particles. Well, it was proposed that the nucleus itself could actually have energy levels. And if it was possible, this thorium daughter nucleus could be left in an excited energy state and take some of the energy, a discrete amount of energy, from the alpha particle, and that's why the alpha particle wasn't going as far. So if you can sort of think of this as being there's your zero energy level, there are other levels here that this could exist at in mega electron volts, and it's possible the daughter nucleus might have been up here somewhere, and therefore the alpha particle is missing that energy. Now, to prove that then, or sort of confirm that, what would happen then is this daughter nucleus would then drop down to its lower state, its more stable state, and release energy in the form of a gamma ray photon, equal to the missing energy here, and that's what happens. And it's possible to be left in a second excited state there and release 2 gamma ray photons, or a really big one. So gamma ray photon production is associated with these alpha particle tracks, and it's evidence that the nucleus has to have discrete energies because the lengths here are discrete, and therefore it's missing discrete amounts of energy. Now you can see evidence of these sort of alpha particle tracks being discrete lengths here. This is the alpha tracks from radium here, and you can also see these here coming off in a cloud chamber, and they're discrete lengths anyway, a particular length there or a particular length there. Okay. So what we've got here is from Frostbite Theatre. They've got a pin there with a radioactive source at the end that releases alpha particles that have got a double positive charge. Now they cause ionisation of the particles of air as they go through there, and what we've got here is alcohol vapour sitting there, which is very cold due to the dry ice underneath. Now that alcohol vapour is able to condense around those ionised air particles, showing you the trail of alpha particles they go through. You can see those alpha particle tracks there. They're quite thick because the alpha particles are quite large, so you get a fairly dense trail going through there because of good ionisation as well. And what we can see here is a nicer diagram of that line of stability coming through here, and it rising in terms of the number of neutrons that are there. Okay, thank you.